So this is a formula for the time it takes to do one swing of a pendulum. So let's establish the relationship between the time it takes to do one swing and the strength of gravity. So what happens if I double the strength of gravity? So I want to know the relationship between time it takes to do one swing and gravity. If I double the strength of gravity, what happens to the period of a pendulum? Will it get multiplied by 2, or will it get multiplied by 2 squared, and so on? I'm trying to establish if t is proportional to g, or if t is inversely proportional to g, and so on. I'm trying to establish the proportional relationship between the two. Okay, so let's try and investigate. So to do this, we need to set up two systems. One system has a gravitational pull of g, and the other one, the length of the string will still be the same, but this time we want to double the strength of gravity. So this will be 2g. So the time it takes to do one swing for this second pendulum will be 2 pi root, remember the length of the string stays the same, but this time gravity for this system will be 2g because it's twice the strength of gravity of this string here. We want to see what happens to the period of a pendulum. So using algebra, we want to get it in the form of something multiplied by the old time. This was the old time. So for example, if I know that there's a 3 here, then I know it's going to be 3 times as long as the old period. If this is, let's say, 5, then you know that the time it takes to do one swing would be 5 times as much as the old period. If this is, let's say, 1/2, then you know the time will be twice as quick. It would be twice as quick if it's a fraction here, and so on. I want to get it in the form of, I'm just going to use algebra to get from here to here somehow. Okay, so hang on. So using algebra, remember, if you square root a over b, that's the same as root a over root b. So use on this, that would then be 2 pi, imagine this as a block, equal times root L over root 2g. And then using root AB being the same as root A times root B, I can use that to break this up. So that would be 2 pi as one block times root L over root 2 root G. So now, so you've got this fraction here. Using algebra, I can break this fraction up as 2 pi as one block times 1 over root 2 as one block times root L over root G, using algebra, because top times top, bottom times bottom will give you this. So now, let me clean this up. So now, remember the aim was to rewrite it in terms of something times the old time. This was the old time here. Okay, so we want to get it to something times this. I'm going to extract this block and put it in front. So it looks like this: 1 over root 2, 2 pi, and then root L over root G. I'm just moving this block to the front, and then if given this, you can jump backwards to get back to its original. So I can get back to its original by square rooting the fraction. So that would be root L over G. So you see, this is the old time, and the new time is given by the old time times this. So what that means is, if you go back and look at the relationship between the time it takes to do one swing and gravity, if you double gravity, if you times this by 2, then you actually divide this by root 2. If you use the same algebra, if you triple the gravitational pull, then you would divide this by root 3. But the thing is, we don't use divide here. We use times 1 over root 2, which is the same as divide by root 2, and then times by 1 over root 3. The reason why I'm doing this is because you can see, if you visualize it like that, you can see that the relationship is inversely proportional to the square root of gravity. That is your relationship. Your proportional relationship is inversely proportional to the square root of the gravitational pull. Okay?